So we're going to be incorporating a little bit of chemistry into our course. So, today we're going to talk about the Kirov structure of our relationship. Named after Kirov, who proposed the structure, how to represent relationships. So, in relationship theory, we represented it via graphs, either directed or undirected. And then, for the Kirov structure, we will be representing them in terms of the Lewis structure of a chemical compound. So, So the first thing we have to do is, the thing is, the Kirov structure is sort of an arbitrary thing or object. So given a relationship, what we have to do is correspond each member of the relationship to a certain element on the periodic table. Now the easiest to work with is carbon, hydrogen, and oxygen. And the most important thing that you guys need to know about these three elements is their valence electrons. Or how many valence electrons each one have. Because that will be important when we start drawing the bonds between these three elements. So, how many valence electrons does a carbon have? So we know that the valence electrons of a hydrogen is 1. Oxygen, if I remember correctly, it is 6. And then carbon is 4. There, yeah. I think this is it. So the amount of valence electrons of a chemical or of an element is basically how many electrons it can expend when bonding with another element. So to construct the Lewis structure of a chemical compound, let's say carbon dihydrogen, CH2. So basically what we do is determine the element with the most valence electrons and put it in the center. So this, in this case, carbon has the highest. And then we draw the valence electrons as dots around it. So 1, 2, 3, 4. And then we draw the rest of the elements. So since there's 2 hydrogen atoms here, H and another H. Now since hydrogen only has 1 valence electron, we do it here, we do the dots over there. And then you notice that these 2 dots here, there's exactly 1 dot here and exactly 1 dot here. So what we do there is replace with a line. So replace with a line. So this is the Lewis structure of carbon dihydrogen. Okay. So that's carbon dihydrogen. So okay. So okay. So let's correspond. Okay, let's correspond oxygen with a person. So oxygen oxygen, hydrogen,
It's our
carbon.
last album, and I'm pretty sure you're gonna like it if you like those two songs.
Okay, so let's use oxygen this time. So oxygen represents
I think you like
meal, and then let's say that hydrogen is a female. Okay, so here's the thing. What we want to do when trying to represent a relationship is represent, or at least try to abstract or symbolize the sort of strength of each relationship. So we've done that via the shadiness of the graph, or of the edges of between two vertices in the graph. So here, what we want to do is represent the strength of a relationship via the bonds between chemical compounds.
Nah, you just know, miss.
Okay. So let's represent a two-person mono relationship in terms of, or let's construct rather the Kirov structure of a 2p mono relationship. So we have one M, then we have one F. Now, since we correspond each of these to an element, we have corresponding with the corresponding valence electrons. So since oxygen has 6 valence electrons and hydrogen has 1, 6 dots around here. 1, 2, 3,
Valentine's
5, 6.
not like
And then F has 1 valence electron, 1 here.
baby blue shades.
So
It's kind of weird.
balance it out. Draw a line.
Thanks, bro.
1, 2, 3, 4, 5. So this is the Kirov structure of a monogamous relationship between a guy and a girl. Alright, so how about a polyamorous relationship? How do we, let's do a,
Where?
so this is a 2p mono between an M and an F. Now let's try to create the Kirov structure of a 6p
House, bro. It's a fucking
poly
hotel lobby.
of M. So let's create the Lewis, the Kirov structure of this relationship. So now, since we only have an M here, that means we have 6 males in a polyamorous relationship. So each M is correspond to oxygen, so that means it has 6 valence electrons. So let's write it out. M, 2, 3, 4, 5, 6. And then, so now here's the thing. We can opt to only do one bond, but we want to take up as much valence electrons as possible. So what we want to do is instead correspond 2 valence electrons per element, or per male here, and instead we have a double bond between these 6 males. So 1, 2, 3, 4, and then 5, 6. 1, 2, 3, 4, 5, 6, 5, 6, 4, 6. So you notice that when we create a compound, the valence electrons per element here stays the same. It's constant. It always stays 6, and it has to be balanced. So notice that we have a double bond between these two. So let's just take a snippet. Let's take this relationship here, sub relationship. 1, 2, 3, 4, 5, and 6. 2 bonds balances out with 1, 2, 3, 4, 5, 6. Oh, sorry. This is wrong. 5, 6. So yeah, this is a balanced one. Sorry, let me rewrite that.
From or for?
From. Sorry. There, that's balanced. There. This is the rebalanced one. So you notice that this one here is the valence electrons for both of these are equal, we just sort of replaced it with a double bond in order to maximize the valence electrons between these two, that these two will share. So that is the Lewis structure of a 6p poly M. Alright, so how about, let's add another gender. Let's say non-binary. So I'll correspond it to a carbon element. So I call it N. So it's neither male or female, it's some new gender. Okay. So recall that the carbon has 4 valence electrons. And let's draw the Kirov structure of a three-person poly relationship of M and N. Okay. So the thing that makes this a bit ambiguous is that, okay, we have 3 people in a poly relationship, and then they are either male or non-binary. The problem is, which one here is a male and a non-binary? How do we specify that? And this is another reason why we specified the Kirov structure and draw the graph of this. Because we want to specify exactly what are the elements in this compound or this relationship. So,
First time, hell no, bro.
3 people, okay, let's say this time that it's 2 males and then 1 non-binary. That's exactly what we need to draw the Kirov structure. So, I have 2 males, non-binary, another male, and then this is 4 electrons. So, it would, you notice that it would become a double bond because it's precisely 4. And then 3, 4, 5, 6, 6, then bridge the gap to make a double bond. So right now, we don't quite specify yet how strong the relationship is between these 3 elements of this relationship. So what we want to do is make a new notation that is justified by tomorrow's lecture. Okay, tomorrow's lecture will be in relationship theory about differential equation, but we will specify it. So, okay, let's use that notation that I will use. So, I'm gonna erase this, and I will reuse this 2p mono relationship and draw the Kirov structure again. Yeah, 1. Okay, there. Okay, so how do we specify the strength of this relationship without having to affect the valence electrons of each element in this, in the relationship? So what we do is make a measure between, I suppose, these 2 constituents and the real number line to construct a function. So there would be a bit of math you need to construct this thing if you want to specify the strength between these 2 constituents of the relationship. And that would be, so if you want to say that these 2 are really strong or have a really strong relationship, we use that sign infinity. So this demonstrates a very strong relationship between, or this symbolizes a very strong relationship between a guy and a girl. So another way of showing it is by some integer a. There. So it could be 2, it could be 3, it could be 4. So it is some abstract notion or abstract measure between these 2, and yeah. So one way to think about it is if we demonstrate these 2 as some vectors, so V1, and then this one's V2. If I take the inner product between these 2 vectors, so I take the transpose of this vector and then take the inner product. This will be the result of taking the inner product between these two. And that will be precisely what we're going to discuss tomorrow with differential equations in relationship theory. Where you find the vectors is at a certain time t between these two by constructing a differential equation for two constituents in a relationship or more, and then solving that differential equation via matrix exponentiation. So, it's a loose structure.
91%.
So, any questions?
Nope.
Nope. Questions?
That's scary.
Alright. So, what we can specify is that A here, which you put on top of the bond, doesn't necessarily have to be an integer. It can be a real number, to be honest. And if your two vectors are ranging over the complex numbers, or C2, it can be complex. So, that's one thing to do. But best not call it's best not to call a relationship imaginary or complex, because that's kind of mean. They're called imaginary. So, yeah. Whew. Can't believe I was able to do that in 16 minutes. So, yeah. That's a good place to stop.
I mean,